Alrighty. Today, we talk about amplifier circuits. And we're going to start off very generally and move towards operational amplifiers. So, let's say that I have a signal. Varies in time. Like so. And this signal could be representative of a voltage waveform, a current waveform, or a power waveform. If I want to make my signal larger, where this output signal could also be a voltage, current, or power waveform. I have two methods that I can utilize. The first method is utilizing an amplifier, which you guys are probably at least moderately familiar with. And the second method is the use of a transformer. And I mean an electrical transformer and not like an Autobot transformer, obviously. So where might you guys have gotten some experience with amplifiers? And I don't mean like analyzing them in circuits one. Like where in your everyday life do you think you might use amplifiers? Stereos, yeah. Absolutely. So the signal that your radio receives from a broadcasting station is actually pretty small, like on the order of a few millivolts. And that signal, after it is demodulated, it is then amplified considerably in order to have enough power to drive the speakers so that you can hear it. That's one of the big things there. So what you would consider a stereo would actually be two types of amplifiers. You would have a voltage amplifier and then also a power amplifier. So the voltage amplifier amplifies the signal to be large enough that you can do something with it. And then the power amplifier is used to give that signal enough power to drive your speakers and stuff like that. Do you guys know where you may have seen transformers or anything like that? So they're not on a what you mean by a circuit breaker is probably more technically a load center, and they're not really located there, although they are connected to. So, pardon? A microwave, absolutely. Yeah, there's definitely a transformer and a microwave oven. The most common transformers would be found effectively all around. Like if you look on a utility pole outside of here, there are transformers. And the reason for that is that, say in Nethkin Hall here, we have a 208/120Y three-phase power being fed to the building. And that probably doesn't mean a whole heck of a lot to you guys yet, but by the end of the class, it actually will. So the voltage that's coming out of the outlets is 120 volts RMS. But the voltage that's being, the voltage that's being delivered to Nethkin Hall from the substation north of town is, I want to say, 13.5 kilovolts. So 13.5 thousand volts gets transformed down to our usable voltage here. The reason why we send voltages over long distances, when we send voltages over long distances, we use very, very high voltages, is because in a transformer, if you step the voltage up, the current goes down. So if you transmit a very, very high voltage, you're transmitting a very, very small amount of current. And when you have a small amount of current, the resistive losses in the lines are smaller as well. So it makes economical sense to send high voltage signals over large distances. And that's something that we'll circle back around to more at the end of the class. So real briefly, I would like to talk about the differences between amplifiers and transformers real quick. So an amplifier is an active device. Does anybody know what I mean by that? Actually, kind of the opposite. Requires power, exactly right. So it requires power in order to operate. So like a resistor, capacitor, inductor, and even transformers, they're all passive devices, meaning that they exhibit their, resistive, capacitive, or inductive quality, whether or not you supply power to it. Like if I take a resistor in a circuit or out of a circuit, it's still a resistor. But if I take an amplifier in a circuit or out of a circuit, once it's out of the circuit, it doesn't do anything, right? It can't amplify the signals without having some external power making it work. So transformers are passive devices, meaning that no external power is required. And as a consequence of amplifiers requiring external power, the output power does not necessarily have to be equal to the input power, because it can take power from outside of the system. Whereas for a transformer, our output power must be less than or equal to our input power. In an ideal case, our output power would be exactly equal to our input power. But typically speaking, there are losses associated with transformers because they're made of wires and things like that have finite levels of resistance. So we are going to focus for the next, I think, 5 or 6 class meetings on amplifiers. Way at the end of the class, we might talk about transformers a little bit. That's the first topic that you really get into in Circuits 3 is the transformer. So the role of an amplifier is an electrical circuit or device which increases the magnitude of the signal applied at its input. So the universal symbol for an amplifier is a triangle. Honestly, not entirely sure why. So if we have some input signal x of t, we expect to get some output signal y of t is equal to a times x of t, where A is the gain of the amplifier. That just means the gain is a dimensionless quantity, usually, that represents how much the amplifier is able to scale the input signal. So, we are going to be looking at amplifiers, at least for a bit, as a black box circuit. So another way that we could represent this exact same thing let's say that we have an input signal x of t. Again, this could be representative of voltage, current, or power, and an output signal y of t. This is our black box amplifier. And our gain is simply the ratio of the output signal to the input signal. And that's going to let us classify a few different types of amplifiers. So I'm going to make a simple table here. The most common type of amplifier, and the one that we're going to focus in this class on the most, takes an input voltage and converts it to an output voltage. And very uncreatively, we call this a voltage amplifier. So the gain of this would then be the voltage gain having units of volts per volts, okay? So an example of a voltage amplifier would be in your cell phone, the thing that converts the signal from the cell tower boosts the level before it goes into the multiplexer and all that kind of stuff for your radio. That would be a simple voltage amplifier. Another place you might see a voltage amplifier, I don't know how many of you guys play guitar or anything like that, but the input stage of the preamp section of your amp is a voltage amplifier. It also contains some analog signal processing circuitry to be able to mess with the tone, which would be the frequency response of the circuit as well, but it boosts the millivolt level signal of your electric guitar to a regular volt level signal that can be processed by the actual amplifier circuit. All right, then we have current at the input. We get current at the output, so that is a current amplifier, pretty easy. If we have a voltage input and convert it to a current output, that is a transconductance amplifier. Almost all BJT and MOSFET amplifier circuits would be classified as transconductance amplifiers because the voltage that you apply at the gate or base of the device respectively is used to control the output current flowing from the drain to the source for a MOSFET or from the emitter to the collector in a BJT. Then we have types of amplifiers where if we put a current in at the input, we get a voltage at the output. That is a trans resistance amplifier. And then lastly, if we get power at the input converted to power at the output, that is a power amplifier. So those are the 5 different types of amplifiers with regards to input versus output signal. There are lots of other different ways to classify amplifiers, what you'll learn about in probably mainly your electronics class, about class A, class AB, class B, class D amplifiers and all that kind of stuff. And all that really means is how efficient they are at converting their input signal to their output signal. So if it's a very high efficiency, it's usually a class A. If it's a little bit lower, it's AB, etc. Not anything you need to worry about in particular right now. So, yeah, all right. So let's consider a simple voltage amplifier circuit. So I'm going to have some voltage source, Vs of t, connected to some resistance Rs of t. So I'm treating my voltage source as a practical voltage source because we're going to be dealing with practical operational amplifiers. That is in turn connected to my black box amplifier. Which has some voltage gain AV. And then I'm going to use said amplifier to drive a load. So let's call this guy RL, simple load resistance. And so this is VL of T. And I'm going to specify a couple other things here real quick. This voltage at the input terminals of the amplifier is, we're going to call it Vn of T, fairly unimaginative. And the voltage drop across the output terminals is then going to be V out. So we can break this circuit down into 3 distinct portions. Right. On the left-hand side, we have our source. In the middle, we have our amplifier. And on the right-hand side, we have our load. So these are 3 discrete parts of a complete amplifier circuit. So let me ask you guys a question. What is the desired or ideal behavior of this circuit? And what I mean by that is, what's this thing supposed to do? Right? So what we want is for our load voltage, VL of T, to be a scaled version of our applied voltage Vs of t. So we want VL of t to be equal to A times Vs of t. That's the ideal case, okay? In reality, it's probably not going to work exactly like that. And we'll talk about exactly why that is, okay? So if we disconnect our practical voltage source at the input of this thing and look into the terminals, what should we see? So what we're doing is trying to find the Thevenin equivalent by looking in from this set of terminals. So again, based on your knowledge of circuits and all that kind of stuff that you learned in Circuits 1, we have a circuit. We are and we are looking in through the terminals where the source was. What should we see? We're disconnecting just the source and looking in through the input terminals of the amplifier while they are connected to that load resistance. It shouldn't be nothing. It should be, so we're looking for a Thevenin equivalent that doesn't have a voltage source because there's no voltage source anywhere in the circuit. So we're looking for some Thevenin equivalent resistance, okay? So if we look into the input terminals, we see an equivalent resistance that we're going to call Rn. What do you think will happen if we disconnect the load and look in to the output terminals of the amplifier? We should see a Thevenin equivalent circuit, right? Having a voltage source in series with a resistor. Practical voltage source. And this practical voltage source is going to be a little different than what we would traditionally expect, and I'll explain why that is, okay? So I'm going to redraw my amplifier circuit. We're no longer going to treat it strictly as a black box. I probably need to make this a little bit bigger. Here's RL, here's VL of T, here's V out, here's V in, here's RS. So none of this stuff has changed. And again, we can say, that's the wrong color, not that it particularly matters. Everything to the left is our source. Everything to the right of the output terminals is our load. Everything here in the middle is our amplifier. So when we looked in from the input, we saw an input resistance Rn. And when we looked in from the output, we saw a practical voltage source. And I'm choosing to use a practical voltage source with a dependent voltage source as opposed to an independent voltage source. This will be our output resistance R out, which is just a Thevenin equivalent resistance. And this guy right here is our voltage gain multiplied by Vn. So what I am saying by putting a dependent source there is that there's some sort of coupling. I'm effectively explaining the amplification, right? So my input signal is being amplified by some scaling factor, and that is composing my dependent voltage source. Then that is connected to my output resistance. So I still just have a Thevenin equivalent practical voltage source there, but I'm also making sure to include the amplification that's happening because it's an amplifier. So we kind of need to take that into account in some shape or form. What I've drawn here in the middle is what's known as the practical model of an amplifier, okay? Any amplifier can be broken down into a circuit like this, which is governed by 3 simple parameters, okay? So any amplifier can be characterized by 3 parameters. The input resistance R in, the output resistance R out, and the gain A. So these 3 pieces of information are what we are going to use to analyze practical op-amp circuits. Now, I'm going to show you guys a schematic diagram of the internal workings of an actual op-amp. This is a Texas Instruments MU-A 741 op-amp, one of the most common op-amps used in signal processing, general purpose signal processing. We can see down here, it has a component count of 22 transistors, 11 resistors, 1 diode, and 1 capacitor. We would be extraordinarily hard pressed to analyze this circuit. In fact, we wouldn't be in your EE curriculum here at Tech, you won't even get close to this unless you happen to take my course on integrated circuit design as one of your electives when you're a senior, okay? This is, analyzing something like this is pretty much well beyond what any employer would ever actually want you to do unless you were going into designing this thing, okay? This is very, very complicated, right? You guys can't see it, but there's like 6 current mirrors in here doing things that are biasing circuits, which are allowing the output voltage to swing from the positive power supply rail down to the negative power supply rail. There's circuitry in here for biasing the circuit to get rid of errors in the manufacturing process, all that kind of stuff. That's well beyond what we would ever need to talk about in a circuit theory class. So we can break this guy down into those 3 discrete components. And if we go back into the data sheet, I probably went too far. We can see that it specifies things like the supply voltage. These are the maximum ratings and all this kind of stuff. Let me find it. Thermal information, no. Electrical characteristics. So we're given things like the large signal voltage gain, the input resistance, the output resistance, all that kind of stuff. The manufacturers tell us those pieces of information that we can apply to our simplified practical op-amp model so that we don't have to use that terrifyingly large thing full of 22 BJTs and all that kind of crap to design any simple circuit, okay? So we're looking at it significantly more, we're looking at amplifiers significantly more in depth than we did in circuits 1, but we're still nowhere close to what you'll eventually be able to do. All right. So let's circle back around to okay, place to do it here. All right, operational amplifiers. All right, so the practical op-amp model for an operational amplifier is very slightly different than the practical model for a general amplifier. And the reason for that is that an operational amplifier is what's known as a differential amplifier, meaning it doesn't amplify a single input signal, it amplifies the difference between two input signals. That's why op-amps have a non-inverting and an inverting input terminal. What's actually being amplified is the differential signal. So with that in mind, I'm going to draw the practical op-amp model for, the practical model for an op-amp. So we have our input resistance. This terminal I'm going to label as V+. So this represents the non-inverting input terminal. This terminal is V-, so it is representative of the inverting input terminal. Down here is my ground, or my reference. Here is my output resistance. And then I'm going to call this AVOL. So this is my voltage gain, but it's very specifically the open loop voltage gain. Okay. And then finally, and this is multiplied by VD, the differential input voltage, which is always the voltage present at the non-inverting input terminal minus the voltage present at the inverting input terminal. So let's define VD here. And then the potential difference between my output terminal and ground is my output voltage. So this is how we are going to represent the model we used in circuits 1, at least until we get more comfortable with it. Okay. So this is our operational amplifier model for the next couple of days at least. So before we jump into any real circuit analysis, it might be useful to get comfortable redrawing op-amp circuits to utilize this model, because that's a very common mistake that I see students make. So let's take, a couple of minutes and do that real quick. So let's say that I had a simple inverting amplifier. I have some feedback resistance, RF. I have some, we'll call this guy R1. I hesitate to call it an input resistance because that's going to get confusing. Here is our load resistance, RL. We're going to ground this terminal, and we're going to apply an input voltage at this guy. And so this is the voltage V minus, sorry. The voltage present at the inverting input terminal. Here's your voltage present at the non-inverting input terminal. And here is the voltage present at the output terminal. So our goal is to redraw this so that we could do some analysis. And I can, just for the sake of argument, let's actually go through the steps and do some analysis here. So let's say that RF is 10 kilo ohms, R1 is 5 kilo ohms, and RL is 8 kilo ohms, and VN is, let's say, 0.5 volts. So those are all the parameters of our circuit. Now we need to know the parameters for the op amp itself. Let's say that Rn is 100 kilo ohms, which would actually be small. Traditionally speaking, the input resistance of an op amp is on the order of 2 to 5 mega ohms if the op amp is designed using BJTs or bipolar junction transistors, and it's on the order of 1 to 2 tera ohms, so 10 to the 12 ohms or a million mega ohms if it's based on a MOSFET amplifier scheme. And let's say that our output resistance of the op amp is 1 kilo ohm, which would be significantly larger than what we would ever see on an op amp's data sheet. So for example, the MUA 741, let's see, R out is 75 ohms. So 1 kilo ohms is much, much larger than we would expect to see. I'm trying to illustrate something by using garbage values here. And our open loop voltage gain will be 10,000, 10 to the 5. Yeah, the open loop voltage gain of most op amps for general purpose operational amplifiers is on the order of a few 100,000 to a few million. So this is a little bit lower. Now, this is a circuit that we could absolutely analyze using our Circuits 1 knowledge, right? What should we expect the output voltage to be based on what we know from Circuits 1? So this is an inverting amplifier, which means it has a voltage gain of negative RF over R1 multiplied by our input signal. So negative RF over R1 is -2 multiplied by our input signal of 0.5 volt means we should expect the output voltage to be somewhere close to -1 volt. Anybody got any disagreement with that? All right. So just as a side note, we're expecting V out to be approximately -1 volt. All right, now let's draw this thing using the practical model. And so how I usually do this is I start by drawing the practical model itself and then connecting things to it. So here's Rn. Here's AVOL times our differential voltage VD. Here's R out. Let me move this guy over a little bit. And here is our ground. So let's start with something simple. Where should I put my load resistor? So the load resistor, we can see RL, or maybe it'll be easier if I do it this way, is between the output terminal and ground, right? Does anybody not see that? So I'm going to go out on a limb here. I'm going to put my load resistor between the output terminal and ground. So this will be my output voltage, V out. Anybody's mind blown by that choice? Hopefully pretty straightforward once you think about it a little bit, all right? Now, what I am trying to decide here is whether I want my non-inverting input terminal to be here or here, because I can change. It's literally just going to make it slightly simpler to draw. That's all it's going to do. VD is still going to be defined as a potential difference between the non-inverting input terminal and the inverting input terminal. It's just going to say which way makes it slightly easier to draw. What I mean by that is I'm going to have a feedback resistor, right? A feedback resistor is going to be placed between the non-inverting input terminal and the output terminal. So do I want to come around all wonky like that, or do I want to connect the resistor like that? Probably the latter one, okay? So let's call this terminal V minus and this terminal V plus. We'll go ahead and do my output resistor, or excuse me, my feedback resistor. So this was V minus. So I have a resistor placed between my inverting input and my output terminal. So this is my feedback resistor, RF. I have my resistor R1 is placed between my inverting input terminal and the node point connected to the positive polarity terminal of my voltage source. So I'm going to tack that guy on over here. So this is R1, and my voltage source is between that node and ground. So is everybody okay with what I've connected to my inverting input terminal? Anybody see any problems or anything, or need me to explain why I drew this the way I drew it? Everybody okay? All right, so what's the last thing that I need to do? Well, I need to connect my non-inverting input terminal to ground. So, done. So in this case, flipping those input terminals, so to be clear here, this is my differential voltage VD. So by effectively turning this resistor over, I simplified the way I can draw this a little bit. It wouldn't have mattered if I had done it the other way. Just to be clear, I would have wound up having a resistor like this. That's just ugly and I don't like it. That's the only reason I chose to flip those input terminals. It's just because I like it to be prettier, okay? So you don't have to do it by any stretch of the imagination. All right, so we now have a circuit. Do we have the skills and capability necessary to analyze it? Let's start there, right? Really not terribly difficult, okay? It's a DC circuit, which is good for us because we probably have the most practice analyzing DC circuits. I guess technically we could use mesh analysis, but mesh analysis is very rarely used in op-amp analysis, particularly ideal op-amp analysis, which is what we did in circuits 1. So I'm going to hold to that tradition, and we're going to do nodal analysis here, okay? So we have, let's see, We're going to do it at this node, which will give us one equation. We know what the voltage present at the non-inverting input terminal is. It's ground, so we don't need to do one there. And then we're also going to have to do one here at the output terminal, and that should be enough information for us to solve for the out, right? So we apply KCL at node B minus. We're going to have our unknown voltage V minus minus our known voltage of Vn, which is half a volt, divided by our resistor R1, which I believe is 5 kilo ohms, plus V minus minus V out, divided by our feedback resistor, which is 10 kilo ohms, plus V minus minus V plus, where V plus is connected to ground, so it's V minus minus 0, divided by Rn, which was 100 kilo ohms, is equal to 0. And then we're going to have KCL at node V out. So let's do the one through the resistor R out first. So that's V out minus our voltage gain, which is 10 to the 5 volts per volt, times V plus, which is 0, minus the voltage present at the non-inverting input terminal, divided by our resistor R out, which I believe I said was 1 kilo ohm. So before I move on to the next steps in this, everybody clear what's going on here. I'm taking this current, right? So it starts at this node, which is V out with respect to ground, minus AVOL, which is 10 to the 5, times VD, where VD is 0 minus the voltage at the inverting input terminal. So that's where that came from. I want to be very, very clear about that because it might seem a little odd. Then I'm dividing that by this output resistance of 1 kilo ohm because that's how I get a current, right? Then I'm going to have the current up and to the left through my feedback resistor. So that's going to be V out minus V minus divided by 10 kilo ohms plus V out divided by my load resistance, which I believe I said was 8 kilo ohms, is equal to 0. So I have two equations, two unknowns. My hand got in the way. What the heck is happening? Give me back my PDF thingy. Why is it not? Oh, if this crashed. Oh, good. I was going to be really pissed off. All right. Okay. So I have two equations, two unknowns. So you guys have calculators. Let's take a moment and solve this guy and see how close our guess, our educated guess of an output voltage of V out is -1 volts is to what our practical op-amp model gives us for honestly a pretty garbage practical op-amp, right? Gain is lower than it needs to be. Output resistance is much smaller than it should be. Input resistance is output resistance is much larger. Input resistance is much smaller. So two equations, two unknowns. So my coefficient for the inverting input terminal voltage is 1 over 5,000 plus 1 over 10,000 plus 1 over 100,000. My coefficient for my output voltage is -1 over 10,000. And my constant term is going to be 1/2 volt divided by 5,000. Then for my next bit here, let's see, I'm going to have negative, so positive 10,000 over 1,000. No, 10 to the 5 is 100,000. Yeah, right. Yeah, 100,000. Minus 1 over 10,000. All right, my calculator didn't like that, so 10 to the 5 is 100,000 divided by 1,000 plus -1 over 10,000. There we go. And my coefficient for V out is 1 over 1,000 plus 1 over 10,000 plus 1 over 8,000 is equal to 0. Solve. So I get 102.218 microvolts for the voltage present at my inverting input terminal. And I get negative 999.683 millivolts for my output voltage. Anybody else get those similar numbers? Let's see.
Yeah, the first one I got here. They got 1.2245.
All right, let me double check. Feel like my answer is correct, but let's double check it. Pardon? Well, the out's the important part. So, I mean, I got 0.000102218 or whatever volts, so that's why I put it in microvolts. But V out 0.9999683 volts, really dang close to -1 volts, right? That's the important part here. So, in this negative feedback circuit, it's a negative feedback circuit because there's a feedback resistor placed between the, I went too far, output terminal and the input terminal. Our practical op-amp model is behaving very, very close to what we would expect for the ideal op-amp model that we used in circuits 1, okay? Which is exactly why we get to use the ideal op-amp model anytime we have a negative feedback circuit. And we'll revisit this in a bit more depth in a couple of days. But if we did a different circuit, the practical op-amp model and the ideal op-amp model would vary extremely differently, okay? Okay. So the goal of this circuit actually was just really redrawing things using the practical op-amp model. We're, I guess, a little bit ahead. No, this will be fine. We're actually good. And I got time to do this. Okay. So let's consider another circuit. Okay, and this one's going to be significantly easier to analyze. all right? Or let's, actually I take that back. Let's make it even easier to analyze and make it the voltage drop over an open circuit. So we know that no current's going to flow through or anything like that. It's going to make this even easier, okay? So this is our circuit. How would we redraw this thing? All right, so let's see, between the inverting input terminal, which is here, and ground, I have my 2-volt source. Between the non-inverting input terminal and ground, I have my 3-volt source. This is going to be AVOL times VD, and technically I should have R out here, but no current actually flows through that resistor, so it's not particularly going to matter. All right, so let's take a moment, and you guys tell me what my output voltage should be. Should be real easy to figure out here. And for the sake of argument, there's our ground. So without getting into the math, can anybody tell me what the output voltage is supposed to be? If no current flows through this resistor R out, V out has to be AVOL times VD, right? So if we use the same values as the last example problem, AVOL is 10 to the 5, right? Is that what we used? Yeah, AVOL is 10 to the 5. So let's just say, oops. Values. So if our open loop voltage gain is 10 to the 5, then what is our output voltage? So what's VD? One volt. 3 minus 2 is 1. So what's 1 times 100,000? 100,000, right? So supposedly we would get effectively a differential input voltage of 1 volt in, and we would get 100,000 volts out, okay? So this is a place where our practical op-amp model is failing us because it does not work that way. If we could effectively create huge voltages this simply, we wouldn't get paid nearly as much as we're going to, or you're going to when you get out of here, okay? So the problem that we have here is that we are not paying attention to one of the topics that we talked about previously in this class, is that well, effectively for an operational amplifier, the output voltage can't exceed voltages. We're not taking into account how we are powering this thing, okay? We have neglected to do that to this point. We're gonna stop doing that, all right? So if, for example, I put 10 volts on the positive supply and negative 10 volts on the negative power supply terminal, then our output voltage would be limited to positive 10 volts or negative 10 volts, okay? This is what's called saturation distortion. So we have an amplifier circuit, and it can amplify very, very small signals, but as soon as we get beyond a certain point, it saturates and pins the output to either VCC plus, which is this 10 volt here, or VCC minus, which is this negative 10 volt supply there, because our output can never exceed our power supply voltages in an op-amp. And that's assuming that we have what's called a rail-to-rail op-amp. Many op-amps don't do that. And so typically speaking, the output voltages are only able to go up to about 1.5 volts below the power supply. So if we look at this guy right here, let's see if we can find some information about okay, yeah. So the supply voltages are between negative 18. I don't know, maybe I should zoom in so you can see it a little better. It's too much. The supply voltages are, we can put up to negative 18 volts on the VCC minus pin, positive 18 volts on the VCC plus pin, but our input signals can't be larger than negative 15 and positive 15 or we get distortion. Okay, so that's what so this is not an example of a rail-to-rail amplifier. So we got let's see. All right, so let me write this down and then we might do a simulation real quick just to show what's going on. So saturation distortion. In a real op amp, the output voltage cannot exceed the power supply voltages. So we would see that V out is going to have one of three values. It will be VCC plus, the positive power supply voltage, when AVOL multiplied by V plus minus V minus is greater than or equal to VCC plus it will be AVOL times V plus minus V minus when VCC minus is less than AVOL V plus minus V minus is less than VCC plus. And finally, it will be VCC minus when AVOL times V plus minus V minus is less than or equal to VCC minus. And these all have special names. So this first condition is positive saturation because we're saturating at the positive power supply terminal voltage. Then we have the linear operation range. So when we're actually amplifying the input signal. And then we have the negative saturation range.